I'm going to talk today about a neglected tropical disease called soil-transmitted helminths. So neglected tropical diseases are extremely prevalent, right? So more than 1 billion people are affected by these, right? Now, affected can mean different things, but there's a lot of people infected at any time. There's a lot of people at risk. I think actually the actual risk is something like 4 billion people, right, at any given moment. So, more than half the planet are at risk for these. There's lots of treatment though, right? And so treatment is in existence, but it doesn't always reach the people who actually need it. And the problem is these tend to be diseases in places of high poverty. So classic ones include river blindness, schistosomiasis, elephantitis, and soil-transmitted helminths. So I'm going to talk about the last one. This is basically worms. Right? Now I think avoided any gross pictures. I think I mostly went with cartoons because, I don't want to put off my audience too much. But these are basically worms that get inside you and it's not fun. Right? Now, the thing about neglected tropical diseases is they don't generally kill you, right? But they do cause a lot of disability. And that disability can be temporary or it can be permanent. Okay, so there is treatment, right? You can basically have deworming. So, I remember being a kid and we got, there was deworming days in school and stuff like that. Now I grew up in Australia where they do have some of these more than we have here. But what happens is we get mass drug administration applied to the whole population, or at least large parts of it. This is given whether people are infected or not. There's no often way of telling for sure. So they will just give kind of all the kids in school some treatment. All right. The important thing is to run these in conjunction with improvements in water, sanitation, and hygiene, as well as infrastructure training and human resources. It's not enough to just kind of have these Western solutions where we just say, well, we've got a drug, we give it to people and kind of hope for the best. These programs work best when you actually engage with people on the ground and kind of in their, in their own language. All right, so in 2015, there were more than 1.5 billion doses administered to almost 1 billion individuals, because some are done more than once a year. Right? This treatment is safe, effective, cost-effective, costs between 30 cents and 50 cents per person in most settings. Some of the other costs are, of course, you need people. Right? So those are sometimes in abundance and sometimes not, depending on where you live. And if the prevalence is larger than 20%, the World Health Organization recommends treatment once a year. But if the prevalence exceeds 50%, then it goes up to twice a year. All right, so depending on the regions, we have different amounts happening. And these are delivered either by school-based programs, as I mentioned earlier, but sometimes community-based programs, because some of these diseases, or particularly some of these worms, infect children primarily, but others don't. Others infect adults as well. All right, so the aim is to cover at least 75% of preschool and school-aged children, but adults are also important drivers of the transmission for some of these, such as hookworm. Okay, so there's two primary drugs. I will not attempt to pronounce them. They're effective at treating some infections, right? So they're good at hookworm and this other one, but not everything. So some of these need a combination of one of those drugs and ivermectin. And these are available cheaply in some countries, but not all. Right? So there's lots of overlapping issues. All right, so the questions that I'm going to look at are basically how many rounds of treatment do we need in order to interrupt this transmission? Could we determine the critical drug efficacy? And could more rounds of treatment make a difference? And I'm also going to tie this into a project that's being done in Kenya. Okay, so here's the model. The model is fairly simple in some ways. So we've got an infectious reservoir inside a human host, right? And then we've got the mean number of worms in the human host, right? There's an infection rate beta, there's a parasite mortality rate, there's an egg production rate lambda, F here is the fecundity, there's a human death rate and also a worm death rate inside the body. Okay, so I'm going to both simplify and complexify this model in different cases. Okay, so here's the basic model, right? And so the worm fecundity here is given by this equation. This is not original. This is a long-standing fecundity equation. And there's a mating probability of adult worms. And K here is the clumping, and Z is the measure of density. So the K here, what that means is that if you have kind of like, a few individuals with a lot of worms, right, then you'll have, I think, a lower K. And so that's going to matter. Are the worms distributed evenly in the population, or are they kind of more condensed in some people? Okay, so one thing we're going to do is simplify this first. And basically the lifespan of the reservoir is much shorter than the adult worm. So we expect that the parasite reaches equilibrium much faster than the mean number of worms do. So we're going to rewrite this model as a one-dimensional equation. And the reproduction number here is basically easy to find from the basic equation. So we have some basic analysis before we introduce the impulses. We've got a disease-free equilibrium. There's endemic equilibria that you can find using this equation here. I'm going to denote stable solutions by m star, and in the graph I'll draw them as solid curves, and unstable solution by dash curves, and that's m lower star. Okay, so there's a bifurcation point which we can find, and we have a reproduction number which we can, there, yes. We can get from the basically the fecundity equation at the bifurcation point. Okay, so here we can see the saddle node bifurcation for different values of the clumping, right? And so you can see as the clumping parameter gets smaller, so that I think ends up being there's more clumping, the mean number of worms gets lower. There's a transmission breakpoint is basically the saddle node point here, right? And what you can see is that the solid curves vary quite a lot, but the dash points don't vary quite as much, and nor do the critical points here. All right, so I mean, obviously they do vary, but like there's much more variation in the solid curves, the way these things fall. Okay, so clumping is a key parameter, and the endemic equilibrium breakpoint becomes smaller as k decreases. So that means you have a few individuals carrying a high burden of parasites, right? So yes, that goes with smaller k. All right, so here's a couple of things we can show. Disease-free equilibrium is always locally stable. The endemic equilibrium is locally stable if the equilibrium value is greater than the bifurcation point, and it's unstable otherwise. There's a local bifurcation. This is separatrix, which splits the phase portrait into two. So solutions starting above go to m upper star, and those starting below go to 0, because the m lower star is unstable. All right, so now we're going to add in mass drug administration. So we're going to extend our model to an impulsive one. Right, so we take a one-dimensional model, and now we're adding in impulses. And what's happening is at certain times, and those times can be fixed or variable, although we're going to consider fixed ones. Yes, so at certain times Tn, we're going to have an impulse. And what the impulse is going to do is it's basically going to reduce the mean number of worms through the drug treatment. All right, so this is the time which we implement the treatment. This is the coverage of the treatment, and epsilon is the drug efficacy. Okay, so here we have the unstable equilibrium is up here, right? And if we start below that, then basically, well, regardless of kind of what happens, we know that we're going to go to 0, right? If we start above the unstable equilibrium, and if you don't have any treatment, then you're just going to go up, right? Or if you have only a small amount of treatment, you're going to go up to the stable endemic equilibrium. But if you have enough treatment, you can see that if you go down and basically pass over the unstable point, then of course you can eradicate. So with sufficient treatment, then great. We're basically looking to kick over that separatrix. Okay, so just to sum up, if we start below the unstable point, then solutions go to 0. If we start between the unstable and the endemic equilibrium one, then we could clear the infection with sufficient treatment. And if we don't have sufficient treatment, or if we start above the endemic equilibrium, then we're going to go to the endemic equilibrium. Okay, so depending on which area you live in, either you're going to have once a year or twice a year, but also sometimes more, depending on how severe the problem is. So we might need more treatment, right? And so if we can have more treatments, then we can eliminate the parasite, right? So the program right now says either once or twice a year, but I'll talk a bit more about increasing that in a moment. Right. So here we're having more treatment happening. Right. So we're basically sort of applying this treatment, and if we can apply it enough so that we kick over the threshold, then great. Right. Now, of course, we need to know when we've kicked over the threshold. Right. It's not enough to just do 2 of these and then stop. All right. We need a few more here. So that was biannual one. Sorry, let me just go back a second. That was biannual. Here's annual. It's a similar story. Just obviously they're spaced out a bit more. All right. So again, if we're below the unstable equilibrium, we go to 0. So we're going to look at the case when we are above the unstable equilibrium, and we're going to use an overestimate to simplify things a bit. Right. So Our overestimate basically says that we're going to replace the fecundity equation, which is a bit more complicated, by this F max. All right, so that's the fecundity at the bifurcation point. All right, so doing that, we can find a bound for the final point in the impulsive cycle. So locally, the Tn minus is the value of the mean number of worms just before an impulse. So that's sort of the local kind of maximum there, and then you reduce the mean number of worms. So then you start with the new initial condition, and oh, sorry, that was the new initial condition from the previous cycle. All right, so we can solve that one. And if R naught times F max is less than 1, then the number of worms decays, and otherwise it grows. Okay. And so after the impulse, then we basically apply our impulsive conditions, and we get a bound for the solution. And I'm going to assume that the impulse times are fixed. This makes things a lot easier if we do that, and also that represents what's happening in reality usually. Now, I'm going to later add in one where it's out of phase, but we'll do that as a separate thing. Okay, so we can find the endpoints of the impulsive periodic orbit, right? So there's the upper and the lower ones. And so once you know the endpoints, basically, well, if you know, with the overestimate, since you can solve it, then you've kind of trapped the impulsive solution there. And we want to now find the number of rounds of treatment that we need. And so if we basically take the local maximum and rearrange and solve for the number of rounds, then we can find exactly what we need. All right. So if we can basically apply this many rounds of treatment, all right, then we eradicate the infection. Okay. All right. So here we see the analytical solution is in red, and the numerical solution is in black. So you can see they're pretty similar here. After a few, they start to diverge a little bit, but you can see that the overestimate obviously is larger. Eventually, we're going to kind of hit the threshold, and then we're good to go. Right. If we look at annual treatment, you can see they diverge much faster. And so in this case, it's pretty obvious here. You can see you need the theoretical prediction says whatever the n you find from the previous one, you need a few more than actually maybe you do in practice, but that's fine. All right, so at least we would obviously be bounding that in the correct direction. So what I'm going to do next then is modify the model in a different way, and we're going to separate the population into people who are treated and people who are untreated. Right? And so I'm now going to tweak this model to say I've got some untreated people, so the non-treated people here, right, and then the treated people, right, and this is all when I'm not at one of the impulse times. The parasite is as before, but I'm going to do the same trick, right? So again, I'm going to basically just say, well, let the parasite go to its equilibrium value, and let's look at just the two populations now, right? And then the impulse conditions are that only the treated group is changing at the impulse. So officially, I've written down an impulse here, but it doesn't do anything. Right? This is I reach the impulse point, nothing happens, so we continue on. But in this one, the number of treated people will be taken out. Right? And so what's happening is, can you get eradication if you're only treating some proportion of the population? All right. So we have a disease-free equilibrium here. All right. There's an endemic equilibrium that we can also basically find by solving that equation. We can prove our disease-free equilibrium is always locally stable. Our endemic equilibrium is locally stable if R naught is less than this here, which is basically derived from the fecundity equation, and it's unstable otherwise. All right, so here we have the red is the mean number of untreated worms. The red dashed. The black star is the mean number of worms overall. So if you basically, start above, then everything goes to the endemic equilibrium, right? If we start between the two equilibria, then we go up to the endemic equilibrium as before. And if we start below, then we go to 0, right? So this is where we're not treating anyone. This is just everything you would absolutely expect. But now so the summary, if we don't have any control, then everything is as before, even though we've got two populations now, all right? And so we know when we have eradication or not, but now we add in our treatment, right? So remember, only some individuals are being treated, right? And well, we want to see how much treatment can control the disease and when does it rebound. So here, it's a little bit more complicated, right? So the star here is the the baseline case where basically you don't apply any treatment. So if we start between the two equilibria, we would go up to the endemic equilibrium, right? And if you look at, say, the purple here, right? The purple is this is sort of like low efficacy treatment. The dashed is the untreated people, right? And the solid is the treated people. So what's happening is we're treating people. So we are treating enough people that we've gone below the unstable equilibrium, but only in the treated class. And then they start to increase, and the untreated also decay because there's a relationship between the two, but then everybody goes back to the endemic equilibrium. Now, in the other cases, say the blue here, right, we are still only treating some people, but we treat more of them, right? And you can see, okay, well, the dashed ones, it's continuous, but now it starts to decrease, and in this case, we go down to 0. And in the red or the black, it's similar case, but it might take different times. All right, so depending on how much you treat or what you treat, I mean, I think actually, sorry, the red and the purple are probably the most interesting because we're treating the same amount, but it's with different efficacies and so on. So it's not just the amount of impulse you apply, it's how effective your drug is. All right, so basically disease elimination occurs if the efficacy or the coverage are high, all right? And infection persists if the efficacy or coverage are low, or if there's no control. All right, so if we apply the same overestimate as earlier, right, then we can bound our equations, and if we apply the impulse and put that in, then we can find our kind of local maximum, and then that will help us rearrange and see that. So you can see that the blue here is the analytical solution of the treated, and the red is the analytical solution of the untreated. Right? So the treated are kind of having their impulses, and those are kind of like they've passed the threshold a long time ago, but the untreated takes some time, right? So for the analytical solution, we need to get the untreated down to here before we can stop. So that's quite a lot of treatment happening. Essentially, the individuals who you're treating are carrying a lot more of the burden of control here. They're going to wait for the non-compliers to kind of catch up, and then the dashed ones are the actual solution from the full model without the overestimate. All right, and with annual treatment, you get more divergence happening, but the story is pretty similar. Okay, so accuracy is better if K and R not are both small. It looks pretty similar, but so I didn't show the graphs. That's true in our case. And the accuracy is better when the frequency of treatment is higher, right? So it's better for biannual treatment in terms of the overestimate agreement, but both are pretty strong alignment, I think. So I just want to talk about some of the pilot studies that have been done. So in Kenya, they did this Tumikia project, and there's about 15 million Kenyans infected with these worms. That's about a third of the country. So it's an enormous number of people, right? And this project wanted to assess which strategy was more effective. So there was a combination of school and community-based treatment or school-based treatment alone. So they had a 2-year project. This is what Tumikia stands for, and I'm not going to in any way pronounce that. There are 120 community clusters in Kwale County, Kenya. 40 were randomized to take part in one of 3 strategies. So there was annual school-based treatment, there was annual community-based treatment, and there was biannual community-based treatment. Right. And I just need a measure of the overall number of worms, because if we have a combination of treated and untreated people, then we just need to know sort of overall what's our worm burden. And we got different outcomes depending on the 2 models. Right. So if the drug efficacy was small enough, in this case less than 44%, then it doesn't work. Right. So the worms remain endemic. And if the efficacy was sufficiently high, then infection dies off. But in between, you get multiple outcomes. Right. So there's some region in between where it's hard to predict. Well, I can predict from 2 different models, but I get 2 different outcomes. Right. And so here, the black here is the untreated and treated individually. The blue here is the mean number of worms from the model with the 2 classes, but the red is the mean number of worms from the model with the single class. Right? And so you can see obviously the blue and the red go to different things. The blue is going to the endemic equilibrium, and the red is going to 0. So the red is the case where we just kind of got a group and we're just treating them all. Right? And the other case is, so we apply our impulse, right, and you can see we're in the black here, we're treating people actually more than we were treating the red ones, right? And so we're obviously applying a fairly high burden of treatment to some people, but of course the other ones aren't being treated enough, so they pull us back to the endemic equilibrium. All right, so yes, there's model 1 and model 2, right? And it's similar for annual treatment. The drug efficacy thresholds have shifted, but the similar results happen. So between 73 and 85%, you get multiple outcomes, right? So there's model 1 and model 2, and it's a very similar story. Okay, so what we propose is an additional round of treatment. What if we just had a bit more treatment, right? And so now the times here are not in line with the previous ones. These are actually some extra times that's actually kind of based on stuff on the ground, right? So if we can increase drug efficacy and do these kind of like, we're doing kind of some regular treatment and then we do a kind of booster shot later, right? And so these are essentially guided by what we can do in the field, right? So you can see that you get your kind of like, you have your kind of regular treatment happening here, and then you wait a while, and then there's an eventual one later on, right? Or similar for the black here, right? And in that case, you can control with this extra shot, right? And that's true for annual treatment as well, right? So for the biannual one, it was 2.5, but we don't have the 0.5 in the annual one. All right, so in summary, we proposed 2 impulsive models, right? One had untreated individuals and one didn't split the individuals in 2. And we see that treatment is not necessary if your initial conditions are below the unstable endemic equilibrium. Otherwise, we can apply sufficient treatment to suppress the worm population. If the clumping and R0 are sufficiently small, then you don't need as much treatment, right? Or if the drug efficacy and coverage are high. Both models predicted eradication if the drug efficacy is high when you apply this to the Tamiki project, and there's persistence if the efficacy was low, but we had different predictions from each model if the efficacies were intermediate. All right. So on the other hand, an additional round of treatment could help out here. All right, so a couple of limitations here. We used the fact that the reservoir went to steady state because of the different time scale, right? So there might be some effects from the transient dynamics. Impulsive approximations assume that the time to peak for a treatment is 0, so it actually takes time for this mass drug administration to be undertaken. Now, I will say that often this time is like a day or 2. Like I think in India they do like it's something like, oh, I don't know how many millions, if not billions of people like treated in like a 2-day period. Like they just have massive programs going on where they can reach a lot of people. So they are probably relatively short, but they're not 0, that's for sure. All right, so another issue is that even if you apply all this treatment, okay, you've reduced the amount of infection in the population, but the eggs can remain viable in the soil for many, many years. So this treatment is not going to get to eradication, right? This is going to, get you down and decreasing, and then you need to do other things, right? So you need to do other things like behavior changes or improvement in sanitation and water and so forth. Right, so a lot of these are spread by like, just kids playing in the dirt, the eggs get under their fingernails, they put their fingers in their mouth and they get the eggs that way. And so, you might have completely sort of reduced the cases in your village to near 0, and then years later, eggs can just pop up. So these other things are also very important. All right, so to address the 3 questions we had, how many rounds do we need? Well, basically enough to fall below the unstable endemic equilibrium. Can we determine the critical drug efficacy? And the answer is yes, if it's small or large, not so much if it's in the middle. All right, could more rounds make a difference? And yes, 1 additional round can. All right, so in conclusion, we recommend that these results be used in conjunction with other improvements. All right, I think sometimes there's a danger of thinking like we've got a theoretical solution that's good enough, but you need to include all the soft science stuff as well. All right, it's not a replacement for them. And because of the multiple potential outcomes, we need careful assessment of the situation on the ground. All right, on the other hand, an additional round of treatment can circumvent these issues. So it's really crucial to identify the appropriate drug efficacy, coverage, frequency, and timing. Okay, so I'd just like to acknowledge my co-authors. Nick Sung Chong was my PhD student, and then this was also joint work with colleagues at Imperial College London. And if you're interested, you can either go to that link or click on the QR code that will take you to my website. And I'd be happy to take questions.